Okay, so today we talk about two things. So I'll talk about the Hodgkin-Huxley equations, which are the equations that are now almost 70 years old, that explain how voltage-gated channels, or describe, not exactly explain, sort of describe how voltage-gated channels create a spike. How they, the actual sort of behavior, how the behavior of the channels leads to this global behavior of a spike. And then I'll talk about, and those are kind of hairy. Those are sort of hairy equations, and so I don't expect you to remember all this. It's kind of like a basic piece of knowledge in neuroscience about how what's a way of sort of describing the dynamics of this channel opening and closing, and it's what you would need to understand if you were trying to make a realistic model of a neuron that actually sort of can imitate what an actual neuron does. There's another easier method called integrate-and-fire that's easier to deal with than Hodgkin-Huxley, and that's commonly used when people are trying to model a lot of neurons. So we'll talk about that at the end. So hang on. So it's just there's some complicated math, and I can't really do it justice, but let's just go over sort of the main equations, and so you just sort of recognize some of the letters, the typical letters that they've been using for 70 years, and get an idea of how this whole machinery works. So what are we modeling? So let's first make a simple electrical circuit model of what we're modeling. And so for the first part here, we're just going to talk about a neuron, just a point neuron. So it doesn't have any dendrites or any sort of spatial extent. It's just like, first imagine a spherical cow. So just start off with sort of like a neuron with just one part, which is good enough to sort of explain some of the dynamics. And so what is our neuron? So our neuron consists of some parts that are kind of like a membrane, and then some return circuit. And so the first part of our neuron is the membrane capacitance. And the membrane capacitance is the thing I mentioned last time, that when you have a thin membrane with charges on either side of it, the charges can sort of pile up and attract the opposite charge across that little thin membrane and stick to the membrane. And so it's kind of like a little reservoir of charges. So that's the capacitance of the membrane. So that's important for understanding the dynamics of how these channels open and close, because it can hold quite a lot of charge temporarily. And then we have sort of like the business end, which is something that an electrical circuit person would draw like that, and that's a variable resistor. So that's our model of a channel. Our model of a channel is a little thing that charges can go through, but the rate that the charges go through is variable. So the channel can open and close. So if it's open, it's low resistance; closed, it's high resistance, and things in between. But then we have something that's actually so that looks different than the capacitor. So that's a battery. So that guy's a battery. That's the electrical circuit model for a battery, and the battery is basically the Nernst potential for a particular ion. So that's the Nernst potential. It could be, potassium or sodium. So that's the Nernst potential for that ion. So that's the kind of like the driving force on that channel that is now going to have a variable amount of resistance, letting varying amounts of current through the channel. So instead of just ion, let's call that one the sodium battery. Okay, so there's the sodium battery. And then this guy is the sodium conductance, that variable resistor. So that's the sodium the sodium channel, like the voltage-gated sodium channel. Okay, so then we have another one over here, and that has a battery going in the opposite direction because that one is the potassium battery, and that has kind of the opposite sign. So here's the Nernst potential for potassium, and here's the variable resistor that does the potassium. Okay, and then of course don't forget about the resting potential channels. You have to put them in there too. So we have, and those channels aren't variable, they're always the same. And so here's the battery for the resting potential. And so that one that has a slightly different Nernst potential because it's a slightly leaky channel, so we call that one Nernst potential leak. And then this is the conductance leak. It's just like a leak, like a water leak. It's always there. Okay, and now that's just a couple channels, but last time we talked about, oh man, look how many there are. There's hundreds of them. Okay, so we can include more, and so that's et cetera. So we could sort of tack more in there. And so that's our electrical model of the cell. And then we need to, we might want to stimulate it. So here's a little power source that can stimulate it. And then we just hook it all up. So this is hooked up to that thing, and then this other side of it is hooked up there. Okay, so this is, this is the voltage that's coming in. Here's the voltage that's coming out, and here's a current that we might say, an external current that we might sort of inject into the cell. Okay, so that doesn't look very much like a neuron. It doesn't, it doesn't have any bulk to it. It just has, these parts, and it has an inside and an outside, quote unquote, but it doesn't have any shape to it or anything. But that's the minimum amount of parts that we need to go forward with trying to understand how these voltage-gated channels work. So how did sort of Hodgkin-Huxley think about this? Because this was 1954. That was like the year that that the initial paper on the DNA structure came out. So people didn't even they didn't even realize, they had never crystallized a channel protein. They didn't really exactly know the relationship between genetic material and proteins, and so it's very early on. And so what was their kind of theory of how it worked? Well, they had a theory that there were little particles that would get somehow sort of stuck in the channel that would control whether or not the channel opened and closed. And so there'd be like an inactivating particle that would be like something that would cause the inactivation, and then they imagined that there were 2 or 3 activating particles, and they did this partly because this is what you needed to kind of make the equations work out properly. So if you have 2 particles, then the channel won't open unless both of the particles, the activating particles, are there. So they imagined there were 6 possible states if you've got 2 activating particles and 1 inactivating particle. and they can either be there or not. That's 6 possible combinations. And so they used, first order chemical kinetics. And so here's all the possible states that we could sort of transition between like this. So you could have, put all these arrows in. So you can go back and forth between all of these. And so only one of these is open. So this guy is open. And so that would be 2 activating particles and 0 inactivating particles. So that's, 2 activating, 0 inactivating. So here's a put activating equals 2, inactivating equals 0. And you can imagine what all the rest of them are. So this would be channel closed because we've got 2 activating particles in there, but the inactivating particle is in there, and then et cetera for all these. Back to here where we have no activating particles. So this would be like, let me put one more in. So this is activating particles equals 0, inactivating particles equals 1. Okay, so that's fundamentally what the equations are trying to describe. And when you first see this, it's just like, what's that? What does that correspond to? So are there particles? No, there aren't really particles. There's the membrane protein, and it opens and closes. The pore opens and closes, and then you've got this inactivating flap, which can come in, which is also voltage sensitive. That's the reality of it. And so you might wonder, why do we still talk about particles? And the reason is because this set of equations is kind of the simplest set of, amazingly, the simplest set of equations that will accurately describe what the spike looks like. So to this day, we still use these equations, even though we know there are no particles, really. I mean, there are particles in the sense of, say, neurotransmitters, or that might bind to a receptor on the cell membrane, but that's not the situation here. The situation here is we've got a voltage-sensitive thing. So there are no particles. That's okay. This is just like a simple way of sort of phrasing the dynamics of kind of the chemical dynamics of these variable resistance pores. And so that's why this Hodgkin-Huxley equations are still used to this day to describe neurons, even though there are no particles. Okay, so let's start off with Ohm's law. So we always start off with Ohm's law. So what is, let's start off with the most basic thing, even before Ohm's law, and that is how we describe this basic circuit. So the capacitance of the membrane, and these are differential equations, unfortunately. So they're equations about rate of change, and so the capacitance of the membrane times the rate of change of the voltage is going to plus any current coming through the ion channels. So this thing is current. This thing is current, capacitive current, C current. So that's current that's going through the capacitor. Now, you might wonder, how can you go through a capacitor? You can't really go through a capacitor, but if you piled up some charges, say you piled up some plus charges on this plate, and those attracted some negative charges on the opposite plate and pushed some positive charges away on the opposite plate, that would look like a current going through the capacitor. It was actually just sort of piling up on the plates and being withdrawn from the plates, but it sort of looks temporarily until the capacitor gets full. It looks like some current has gone through the capacitor. And so this is how we say that mathematically. So this is the capacitive current right there. And that's going to equal this external current. So that's the external current. So it's the capacitive current plus all the ion currents equals the external current. Okay, so now what we want to do is unpack. So the external current, that's something we just stuck in, so we know that number. The capacitive current, we just said this is how much capacitance there is, and so we know that number. We don't know this one. That's kind of like an unknown. But now let's unpack this ion current. And so that's where the particles come in. So here, I'll draw a line there. So that's the most basic equation. So what we're doing is we're sort of putting up equations and unpacking dolls within dolls until we finally get down to something real that at the bottom. So now let's unpack the ionic current. And so the ionic current, so this is a particular ion. So we'll say ionic current for all the ions, but let's just take one ion at a time. And so now we're just writing out Ohm's law. So this is a G with a bar on top of it, which we're going to take to mean max for a particular ion. So this guy means max. So it's the maximum conductance of the channel. So that's just a constant, and then we're going to multiply that by two gating variables that are the particle business. So this guy is squared, and we're also multiplying by this H, and these are the same letters that have been used since 1954, and so that's one of the reasons to put the equations up, which is a good thing. They kept using M and H, and so then whenever you see an M in the context of Hodgkin-Huxley, you know they're talking about the excitatory gating variable. So both of these guys go from 0 to 1. And so what they do is they just multiply whatever the maximum conductance is, and so the maximum conductance kind of defines how much current can get through the channel when it's fully open, and then this is just the amount that it's open in percent, or 0 to 1. So this guy is the activation one. That's involving the activation particles. This is the inactivation one. Okay, so and then this was Ohm's law. So that whole mess is like just the conductance in Ohm's law, but then we've got to multiply. You remember Ohm's law? One way of writing Ohm's law was, current equals conductance times voltage. So here's the voltage, and the voltage is the current voltage, the present voltage across that channel, with the Nernst potential for that channel subtracted off. Because remember, if the total voltage across the channel happens to be exactly the same as the Nernst potential, the same as that battery, then there's not going to be any current flowing. Or if it's the opposite. If it's the opposite of the battery, we'll exactly cancel it out. So we only get current flowing through the channel if there's a difference between the Nernst potential, where the battery is trying to drive the membrane to, and whatever the present membrane potential is. So this guy, this whole thing is Ohm's law. So this guy, let's put it off to the side. So the whole thing is just current equals conductance times voltage. So Ohm's law. Okay, so now we have to unpack these guys, the gating variables, because those are the things that are sort of opening and closing. So draw another line there. Okay, so now the hairy sort of chemical kinetics starts. So now what we want to do is we want an equation for how that gating variable is going to change over time. So that's the rate of change instantaneous rate of change of the gating variable. How rapidly is it occurring? And this depends on the voltage, and what particular time, that you're at. So what is this equation? So there's several ways of writing out this equation. So we write out the first one that kind of looks more like a chemical kinetics equation, that where you've got like something on this side, something on that side, and if something on this side turns into something on that side, if say 20% of this turns into this, then there'll be 20% less on that side. So the whole thing has to add up to 100%. So there's this variable. So alpha is used for the forward rate constant. So that's kind of like, that would be something like one of these guys. And then we have a backward rate constant, that would be beta. So the forward rate constant depends on voltage. So that guy depends on voltage. And it has to sort of add up to 1. So this guy is 1 minus m, and then when we have the backward rate constant, that guy also dependent on voltage, is just multiplied by m. So you have sort of 1 minus m and m. And so here's the forward rate constant for the m variable. And then we have the same thing for the inactivation variable. So that's also depends on voltage and time. And so now we're going to have an alpha h, which is for the inactivation guy, also dependent on voltage, and it's 1 minus h over here. And then we've got the backward rate constant for h, the inactivation variable, times h. Okay, so that's one way of writing these first order chemical kinetic equations out for particles, either 2 particles, 1 particle, no inactivation, etc., all the 6 possible combinations. But the more useful way that we write them out is the second way. So this is alternate way of writing. So this is this is called, first, if you want to Google it, first order chemical kinetic equations. Okay, this was Ohm's law. Okay, so this other way of writing it now gets a little hairier. So now it's the same thing we're writing out, which is the rate of change of that activation variable, which is the guy up here that determines how much you're going to multiply between 0 and 1. You're going to multiply the maximum conductance by to determine how open the channel is. So that's this guy, and then this guy equals m infinity. So what does that mean? So this means the state of the activation variable after we're in the steady state a long time, like for instance, have put a voltage clamp on so the voltage isn't changing, and then just wait until everything dies down and figure out what the state of that activation variable is. That's what that m infinity means. Okay, and that is minus m, and then over a time constant. So a time constant for the m variable, which the time constant is also voltage sensitive. You can see why this is, there's so many sort of highways and byways and things mixed up. Okay, so that's another way of writing that equation, and we've got a similar one. For for dh dt. I won't write it out. dt equals etc. Okay, so now let's unpack these guys. So now we want to unpack the time constant, the voltage dependence of the time constant, and the voltage dependence of the steady state m variable. So let's write out that equation. So here's the equation for that guy, which relates it back to these original equations here. So that equation is the alpha m, so that's this guy, at a particular voltage, divided by the alpha m at a particular voltage, same thing, plus the beta m at a particular voltage. Okay, so that's this. So this guy goes there. Okay, well, we're still not down to the very bottom. We got one last one to go. So what is this alpha m as a function of voltage? So the forward rate constant as a function of voltage. And this guy's the backward rate constant. Okay, so that's something that we can actually, it turns out this value is something that we can measure with a voltage clamp by basically getting a neuron and then setting the voltage clamp to a whole bunch of different states and measuring the current through the channel. So instead of just say moving the voltage clamp from 0 to minus 110, let's just go 0, 5, 10, 15, minus 20, minus 30, 25, minus 40, do a whole bunch of different measurements. And if you do that, you can get out equations that that look something like this. So we need space for 3 different graphs. So let me just put the space here before I invade it. Okay, all good. So what do those graphs look like? So those graphs look, these are graphs as a function of voltage. So this is 0 millivolts here, and say this is like 50 millivolts, and here's like minus 50 millivolts. And so by doing voltage clamp experiments, setting these things to all different, we can actually sort of come up with these curves that look, say, here's the value of that, the overall value of that alpha, and we end up with a series of curves like this, something like that. And so what are those curves? So they're made by recording a whole bunch of different voltages for the 4 variables. And what are the 4 variables? Let's put them in there. We've got, here's the backward rate constant for the inactivation guy, and here's the forward rate constant, the backward rate constant for the activation guy, and this one is the this guy is the forward rate constant for the inactivation, and this one is the forward rate constant for the activation, to get those right. Yeah. And so what are those curves? So these curves are just you need to make an equation that will actually sort of copy that curve. So it's an empirical fit equation. I won't write that out. It's another equation. It's got like about 5 parts in it, but it can generate a curve like that. And so what you do is you do a bunch of measurements, and then at all different voltages down here, and then get a bunch of data, fit a curve to it for those 4 numbers. And so basically that is going to let's just draw one of these. So there's the so this guy here. So that's that. Now we've got down to like the bottom. So that's the voltage dependence of the forward rate constant for the activation variable. Okay, so now what about the time constant? So now we've got the time constant, because there's this time constant here, so we need to unpack that equation. And so the time constant equation for the activation variable is also voltage sensitive. So the time constant changes depending on what the voltage is. So that the equation for that is equal to 1 over the forward rate constant, which itself is voltage sensitive, plus the backward rate constant for the activation guy. Okay, so what do those graphs look like? There's a way of empirically measuring those graphs, and what you see is something we mentioned before. So we sort of finally get back to what we talked about, the spike. The activation has to be faster than the inactivation. Otherwise, if they were the same speed, if the little poor plugger plugged at the same speed that the channel opened, well, yeah, then you wouldn't get anything. And so how is that expressed? You can see that this is in milliseconds here, and this is the voltage, sensitivity again. 0 minus 50 millivolts. And so how does that time constant, so this is the time constant, how does that change? It sort of looks something like this and something like that. So what are those? So this is the time constant for the inactivation. So that's going to be longer. It takes a couple extra milliseconds before the inactivation kicks in and blocks the channel. And then this guy is the time constant tau for the activation. That guy's faster. But it's kind of complicated because you can see that the time constant itself is changing, dependent on what the voltage is. So if the voltage is depending on whatever the present membrane potential is, the speed at which the channel opens is going to be different. So this is tau h. But this main thing here is that this guy's faster. And it's faster so when you open the channel, you get some activation before the inactivation kicks in and shuts it down. Okay, so that thing. So how does that fit in? So this is the voltage dependence of the M. So that's this guy. So let's put this down here. And again, we will have collected some data and from an actual squid axon or whatever in order to fill in that number. Okay, so once we've got that, then what we can do is we can look at the way in which this, what is this variable range between? This variable ranges between 0 and 1. because these gating variables, so these are, gating. And so if we plot out this equation here, we get that equation that I mentioned last time, which looks something like this. So if we put the 0 over here, so this is voltage dependence again, but now what we're plotting out is that actual gating variable as a function of voltage. So whatever the gating variable gets to after a long time, when you've held the membrane potential constant, that's the infinity part, then you get something that sort of looks like this. So these equations are not, when you actually see them plotted out, they're not so bad. So this is the gating variable. It goes from 0 to 1. And we mentioned that the channel is only open in this case. So what is that case? Well, this is when the channel is activated, and this is when the channel is inactivated, because this guy is the M variable, the M infinity as a function of voltage variable. And when the cell is at rest, it's not inactivated. So I'll just, instead of de-inactivated, I'll put not inactivated. It's not inactivated. And as you raise the membrane potential, it gets inactivated. Okay, so not inactivated, inactivated. Inactivated. No, let's put not here. Get this clear. So this is not instead of deactivated, we'll say not activated. So not activated, activated. Not inactivated, inactivated. And the only place where the channel is open is right here. Channel open. Okay, so what are these graphs? So this graph was this guy. And it was there. And there's going to be another version of this for the inactivation guy that will sort of describe that other equation. So now we've sort of finally gotten to the end of the Hodgkin-Huxley. We put up all the different variable names that you will see if you ever look at any paper on Hodgkin-Huxley. We finally got to the end. We didn't describe how you actually use this now. So we've got we collected some voltage clamp data, fit some curves to it. Those curves fit in here, and then we use them to generate this guy, which generates that. But now what? So now what we have to do is we have to simultaneously solve all these equations. So now we need to simultaneously solve all these guys. And there might be more channels. So let's put a dashed line because, other channels. So there, people commonly do this with 10 channels in the membrane, so you can actually, get a realistic picture. So we got to simultaneously solve these because they all have voltage in them, but there's only one voltage. There's only sort of one voltage across the membrane at a given point in time, and so all these channels are opening and closing. They're all voltage dependent, and so we have to somehow sort of find a simultaneous solution to the whole mess. So we simultaneous solution, and what we're doing is, a word for that is to numerically integrate. because these equations are so messy, we can't sort of do like a symbolic integration of the solution to the differential equation. Instead, what we do is we just try to predict a small distance into the future. Look at the state of everything, what the voltage is, what the state of the activation variable and the inactivation variable is, and then predict a small distance into the future. Then go into the future, see what your voltage actually is, predict another small distance into the future. So that's how the programs that you can download will actually work to generate the actual spike. So that procedure, unfortunately, has to be done with a very small time step. So in order to do that, you have to use, small time step. Like, for instance, 1 microsecond. Small time step. For example, 1 microsecond. So that's you can see why this is kind of a nasty problem, because that means you need 1 million simulation steps for 1 second. So it's computationally intensive to do this with lots of neurons. Now, after seeing this, you say like, geez, what could you possibly use something like this for? And so I'll try to give you one example of something that it seems like it could be actually useful for. And so this is an example. Say if we have a neuron. Now, I just described this for a point neuron, but neurons have dendrites. So what you can do is do what's called a compartmental model. So you can basically break up a neuron model into a whole bunch of little compartments and have one of these messes within each compartment. So there's the apical dendrite compartments. So here's all these little compartments and one big compartment down there. And one thing that was observed in real neurons is if you put an electrode in the cell body and stimulate it, what do you see in a real neuron? What you see is you'll see a spike. You'll see a spike sort of heading down the pike here. This is the spike going down the axon. But you'll also see a spike going up this way. So you'll see a spike sort of, heading up the dendrite like that, going that way. And you can just observe that in an individual cell. You just stimulate the cell, it causes a spike, but a spike goes up the dendrite. And when you first hear that, it's kind of like, that doesn't sound right, because if the dendrite spiked, it would no longer be able to do dendritic summation, because the whole idea of the dendrite was like you get a little bit of activation, a lot of activation, and then if you get past a certain threshold, you get a spike. It sort of sums up. But if one of these compartments is capable of spiking the whole dendrite, well, then the summation is off, because you're just like, spiking all the time. But it turns out if you take a real cell, this is the model of the real cell, but if you take a real cell and stimulate with a little patch clamp electrode right up on the top of the dendrite, you don't get a spike going down. So if instead of, so this is the axon, instead of stimulating down here, what happens if we go into one of these compartments and stim? So if we do that, it turns out we do not get a spike going down. So you get a spike going this way, but you actually don't get a spike going down. So that is what a spike going down would look like. That doesn't occur. So this doesn't occur. And so why doesn't it occur? So it doesn't occur because of all this mess. And what's the reason in sort of simple terms? What happens is when you stimulate one of these small compartments, you quickly, because the capacitance isn't very big, you quickly inactivate. So this will cause this H variable to immediately get inactivated from the stimulation. And so it's different than an axon. So with an axon, remember, if you stimulate on one side, it goes it goes this way. If you stimulate the other side, the spike will go the opposite way. And this is asymmetrical because of the way that these different compartments in the cell have different amounts of capacitance. So if you stimulate the cell body, you can get a spike to go up the dendrite. If you stimulate one of the dendrites, you can't get a spike to go down. It's asymmetrical. So if you want to sort of really understand in a mechanistic way how these cells, actually compute, this is the kind of thing you need to do in order to actually make a realistic looking neuron that kind of behaves like a real neuron. It's kind of like the minimum thing. And it's nasty, it's got all these parts, but they haven't changed in 70 years. That's the good part. So they still call it, alpha, they still call it M, they still call it H. Okay, so that was introduction, very basic introduction to the Hodgkin-Huxley. What about something that's a little easier than Hodgkin-Huxley? So there's so that's called integrate and fire. And so integrate and fire, so one of the big problems with the Hodgkin-Huxley equations is because they're so fiddly, and they're called stiff differential equations because they've got these very short time constants, and in order to simulate them, when you're numerically integrating, you have to use a very small time step. And so if you have to do 1 million computational steps just for 1 second, and you've got 1 million neurons, then it starts to slow everything down, because we have to simultaneously, and then what if we've got like 10,000 compartments? So that means we've got to have 10,000 copies of those equations, those Hodgkin-Huxley equations. And so one sort of easier way of dealing with this still sort of behaves reasonably realistic is called integrate and fire. And that gets rid of all the H and the M stuff, but it still preserves some of the main features of how real neurons behave. And so the first, if we're going to connect, this is typically used when you want to connect up a bunch of neurons. And so the first thing that we define is conductance waveform, because now we need neurons to communicate with each other. And what is a common one that's used? Well, it always, all my graphs in this class look like that. And this particular graph is a graph of how a channel that's a neurotransmitter channel, which we're talking about in the main course, how does that neurotransmitter channel behave in time? So this is time going this way. And so the equation for that guy, is the conductance of that guy is a function of time. Just equals alpha A times time again times e to the minus t over that time constant tau. So that's a nice little adjustable equation. You can set the amplitude, you can set how long it takes. So that's going to be how some other cell activates you. So you start off with that, and then instead of doing all the Hodgkin-Huxley mess, we just have a spike function. And the spike function is basically just spike at a particular time. So set the spike function to 1, if the voltage is bigger than the threshold. But also not refractory. And so how are we going to sort of cut the Gordian knot with all those, M and H's and all that mess? And so, and then otherwise 0. So if you go above threshold and you're not in the refractory state, which we'll define, then the spike function is 1. And So what does that mean? Well, the definition of this guy is, if you spiked recently, can't spike. So basically, you just have something that says, if you spiked recently, then you got to wait a millisecond or 2 or 3 milliseconds before you can spike again. We just define that. And so then that wipes away all the complicated Hodgkin-Huxley equations. Then we've got to sort of add these things up. Add up, add up waveforms over time. And so how do we add them up over time? Well, what we're doing is we've got some spikes that came down the pike, like that. And what we want to do is add up those conductance waveforms. And so here's a conductance waveform that gets triggered off, and it's almost down to 0 when another one comes, and that goes up, and then now it's not quite down to 0 yet. And so we add another one on top of that. So these are the spikes over here. And then this is the conductance, total conductance through the channel. And how do you do that? Well, that's a convolution. What I just drew there was a convolution. And so let me just write it out without explaining it. So we basically sort of sum across time whatever that conductance function was times our spike function. There might be a delay in there, but here's the convolution part where we basically have in order to get this out of that single one plus this is the operation. This basically just does that. Okay, minus delay, and then time, across all lambda there. So this is, lambda equals 0, lambda equals. Okay, so that's convolution without explaining it, but it's actually intuitive if you know that it just turns these instantaneous spikes into this waveform. And then finally, so add up all of this type, add up all this type of channel, and then finally do that top equation in the Hodgkin-Huxley one. And that equation was the change in voltage for the next time step is going to be 1 over the capacitance, and then we're going to sum over all the channels, all the different channel types, the following thing. And the following thing is whatever the difference is between the present membrane voltage and whatever the Nernst potential for this particular channel is. So there's only one of these guys. There's only one of these voltages. Everybody sees the same voltage, but every channel has a different Nernst potential. And then times, whatever the present G was from this thing. Yeah, so this guy was defining G as a function of time, and G what do I have? This guy was G hat for. Okay, so this is G at a particular point in time. And so what are this? So this is the present membrane. I'm working down right to the limit here, and this was Nernst. And so this will behave like a real neuron in the sense that as the voltage goes up and down, the amount of current going through the channel, which then the current is voltage, Ohm's law, voltage times conductance equals current, that will sort of behave like a real neuron. So if the membrane potential happens to be the same thing as the Nernst potential, you won't get anything going through. The current could go the opposite way if you're on the other side of the Nernst potential. It does all those real neuron-like things, but it gets rid of the whole spike business. And so how does it work? You sort of integrate away. If you reach threshold, so here's voltage at a particular time going in that direction, here's time. If you reach threshold, you just sort of paste on a spike. We just sort of make a fake spike. And then we say, for this amount of time, you're refractory, instead of doing Hodgkin-Huxley. Just say, like, you can't spike. And then after that, you continue integrating away, and if you reach threshold again, paste on another spike. So this is, paste on spike. That's the technical term for it. So this is HodgkinIntFire. So this is an easier way of making a mathematical model of a network of neurons that still behaves more neuron-like than a typical sort of machine learning model. It behaves more biologically, but it doesn't have the whole nightmare of trying to generate the spike with the Hodgkin-Huxley equations. Now it won't do things properly if you if you go up and down the dendrite, but this, for better or for worse, is an introduction to the kind of things that you might want to do if you were making a model, an actual model, biological model that sort of behaves the way real neurons do. Okay, I think I just got in under the time. That's the end there, David.